now, hold point 3.
Confirmed. Watching the wind shear on approach.
ください。気をつけてください。
Right now, somewhere out in Osaka Bay, the ground beneath one of the busiest airports in Asia is still moving. Not shaking, sinking. And the terrifying part is that the airport was designed with that in mind. Engineers knew the seabed was a thick, unstable layer of soft alluvial clay, so soft one project engineer famously compared it to tofu. They predicted settlement. They planned for it. They spent billions trying to control it. Then the numbers came back and the island started dropping faster than the model said it would. That's the paradox of Kansai International Airport, one of the most impressive pieces of modern engineering ever built, on top of a foundation that behaves like a slow-motion trap. Kansai is not just an airport on the sea. It's a $15 to $20 billion experiment in forcing land to exist where land doesn't want to exist. 2 artificial islands, runways, terminals, rail, and highway connections, seawalls, and a nervous system of sensors that constantly measure tilt settlement and stress. It opened in 1994, 5 kilometers offshore, created to solve a problem Japan couldn't solve on land, noise, space, and politics. But even on opening day, the island was already sinking. So tonight we're going inside the impossible airport, how Japan built an artificial island big enough to land jumbo jets, why it began to subside like a giant elevator descending into the sea. And the hidden war engineers are still fighting every day to keep it operating. Because Kansai's story isn't just, can we build it? It's the harder question, can we keep it alive long enough to justify building it in the first place? To understand why Japan put an international airport offshore, you have to understand what onshore meant around Osaka in the 1980s. The region already had an airport, Atami, squeezed into a dense urban bowl. Flights were loud, land was scarce, and expansion meant expropriation, taking homes, fighting lawsuits, and battling communities that had already carried the burden of noise for decades. Every new runway proposal became a political war. So planners searched for a place where the airport could grow without tearing the city apart. Osaka Bay offered something rare in Japan open space. Build it offshore and you solve multiple problems at once. Noise moves away from neighborhoods. Flight paths become simpler. Land acquisition becomes water acquisition. And in theory, an artificial island can be designed like a clean sheet, perfect runways, straight taxiway space for terminals, and a bridge that connects everything back to the mainland. There was also a safety logic. Japan is earthquake country, but offshore structures can be designed to flex and isolate vibration. And a bay location reduces the risk of certain disasters compared to low-lying inland floodplains. Kansai's designers aim for a facility that could survive quakes, typhoons, and the brutal operating demands of international aviation. The concept sounded bold, but not insane. Japan had reclaimed land for decades. Ports, factories, coastal neighborhoods. Osaka itself had grown by pushing into the sea. If you can reclaim land for a container terminal, why not reclaim land for a runway? Because a runway doesn't forgive the ocean. An airport needs tight tolerances. Asphalt must stay level. Structures must align. Drainage must work. A few centimeters of uneven settlement can become a safety hazard when a 300-ton aircraft touches down at high speed. And that's when the project's biggest enemy appeared. Not waves, not storms, not politics, but the mud beneath the bay. Before any sand was poured, engineers drilled into the seabed and found the nightmare, a thick layer of Holocene alluvial clay sitting immediately below the seabed surface, underlain by older alternating layers. In engineering terms, it was like trying to build a skyscraper on a wet sponge. Japan could either abandon the offshore dream or attempt something that at the time looked almost outrageous: manufacture stable land on top of unstable ground and then keep correcting it for decades. The first rule of building on soft clay is simple: the clay will compress. When you dump millions of tons of fill material onto a seabed, the weight squeezes water out of the clay. As that water escapes the clay, particles pack tighter and the ground settles. That settlement is not a surprise, it's the expected outcome. The surprise is the timescale. Clay is low permeability. Water doesn't rush out, it creeps. Without intervention, settlement could continue for generations. For an airport, generations is not a schedule. So Kansai's engineers had to accelerate the process, force the clay to drain faster so it would stiffen sooner. Their weapon was something that sounds almost too simple for a mega project: sand. They used the sand drain method, drive vertical columns of sand down through the soft clay so trapped water can escape along those columns like highways. Faster drainage means faster consolidation. Faster consolidation means the ground hardens earlier. It doesn't eliminate settlement, but it makes settlement more predictable, and crucially, it brings the worst of it forward, closer to the construction phase when you can plan around it. At Kansai, this was done at mind-bending scale. Under the first airport island, operators describe about 1 million sand drains, roughly 20 meters long and about 40 centimeters in diameter, spaced about 2.5 meters apart. Under the second island, they describe about 1.2 million more. Imagine that over 2 million vertical straws pushed into the seabed just so the mud could breathe out water faster. But even sand drains weren't enough on their own, because you still had to create the island above them. That meant an ocean-scale, earth-moving operation. Massive barges delivered fill. Bottom-dump ships released rock and sand. The island footprint was enclosed by a seawall perimeter, then filled and raised layer by layer until it stood above sea level, high enough for runways, terminals, and storm safety margins. And every layer mattered. Add fill too fast, and you overload the clay, causing excessive settlement or slope failure. Add it too slowly, and the project drags on for years while costs explode. So construction became a dance between geology and schedule. Pour, wait. Measure, adjust, pour again, wait again. This is where the impossible airport starts to feel less like a building project and more like a medical procedure. The island wasn't just constructed, it was monitored like a patient. Sensors tracked settlement. Engineers compared readings to predictions. If a zone sank faster than expected, the plan had to change more, fill here, less there. Different sequencing, different reinforcement. And for a while, it worked. The island rose. The terminals took shape. The bridge connection was built. From the surface, Kansai looked like a triumph land where there was only water. But deep below, the clay was still compressing, and it was about to collect a debt the project could never fully pay off. Once the island existed, Kansai's next challenge was building an airport that could tolerate movement. Because unlike a normal airport built on bedrock, Kansai's ground would keep changing. Not dramatically from day to day, but enough that ignoring it would be fatal over time. So the structures were designed to be adjustable. One of the most important was the passenger terminal, a long, iconic building. But beyond the aesthetics, the engineering goal was flexibility. Sections of the terminal and key support systems were built with joints, tolerances, and maintenance access so parts could be leveled and corrected as the ground settled. Think of it as designing a building with the expectation that gravity will keep tugging it downward. The runways and taxiways had the same problem. A runway is essentially a giant precision plane. If one end sinks more than the other, the slope changes. If different zones sink unevenly, you get bumps and differential settlement that stress pavement and create operational risks. So Kansai's pavement and subbase were built with careful layering and constant surveying. And the airport's designers accepted something most projects hate, admitting maintenance would be permanent. Not later, from the start. Then there was the seawall, Kansai's armor. The island perimeter had to resist waves, currents, and typhoons. It also had to resist something subtler, scouring where moving water strips material from the base, weakening the structure. So the seawalls were built robustly with heavy armoring and geometry, intended to protect against both direct impact and long-term erosion. The airport opened in September 1994. Flights began. Passengers arrived. And for many observers, Kansai looked like a futuristic victory, an international gateway floating offshore. But behind the scenes, engineers watched the settlement data like a countdown, because the clay consolidation wasn't finished. It was merely in progress. In early years, the subsidence rate was higher, exactly what consolidation theory predicts when you load soft clay. The hope was that it would slow and stabilize as pore water pressures dissipated and the soil stiffened. The problem was that slow still meant serious. Centimeters became meters, then more meters. And at some point, the airport's defining engineering miracle, the artificial island started behaving like a sinking ship, except you can't tow an airport back to shore. So Kansai's managers did something unusual. They turned a major airport into a living, continuously corrected machine. And that machine would soon face the moment every offshore structure fears: an extreme storm that doesn't care about your spreadsheets.
It's showing a slight deviation.
Kansai's engineers didn't treat subsidence like a rumor. They treated it like a vital sign. Across the island's measurement points track how the ground surface and deeper layers behave. Sensors report settlement and tilt. And the airport's operators respond the same way a ship's crew responds to ballast they adjust. Sometimes that adjustment is as simple as adding fill where the ground has dropped or regrading pavement so the runway stays within tolerance. Sometimes it involves heavier, more surgical moves, lifting and leveling structures, tightening joints, rebuilding sections of seawall, and reinforcing edges that are getting too close to the waterline. Because the numbers are not small. Kansai's own monitoring reports as of December 2024 put the average total settlement since construction began at about 13.66 meters, with about 9.82 meters of that happening before the airport even opened. And as of 2024, the island was still sinking at about 6 centimeters per year on average. That sounds slow until you remember what airports demand. 6 centimeters isn't a cosmetic issue when you're trying to keep taxiways, drainage gradients, utility lines, and building joints aligned year after year. A few millimeters of uneven movement can crack pipes, distort doors, stress structural connections, and create costly maintenance chains. The most unsettling part is that Kansai's consolidation story did what the textbook said it would. The softer upper Holocene layer consolidated quickly once drainage was accelerated, and then the longer-term settlement shifted to deeper older layers that are thick, stiff, and essentially impossible to improve the same way. So Kansai became an airport where the future is always measured in centimeters. And then in 2018, the ocean delivered the kind of stress test no simulation can perfectly replicate. Typhoon Jebi hit the region and caused major flooding impacts at Kansai, exactly the nightmare scenario for an offshore facility. For critics, it looked like proof that building in the sea was a mistake. For Kansai's operators, it was proof of something else. Offshore infrastructure doesn't get to finish. It has to keep adapting. And yet, this is what makes Kansai's story genuinely extraordinary. The airport stayed in the fight. Not by pretending it wasn't sinking, but by building an entire management culture around the fact that it is. Which brings us to the next twist. How do you expand a sinking airport, build a second island and a second runway, while the first island is still settling? Because Japan didn't stop with one runway. They doubled down. The second island is proof that Kansai was never meant to be a one-time stunt. After opening demand kept growing and planners moved into Phase 2, build a second artificial island farther offshore, and add a second runway. Construction for the new island began at the end of the 1990s, and Runway 2 entered service in the 2000s, an expansion that would be impressive anywhere. But at Kansai, it carried an extra constraint. The ground was still settling under both islands. Phase 2 forced engineers to refine everything they learned the first time. They again faced deep water and a seabed made of very soft Holocene clay, sitting above older Pleistocene layers, exactly the kind of profile geotechnical engineers fear when you're about to dump mountains of fill into the sea. They again used massive ground improvement efforts, including the sand drain method, at extraordinary scale. Kansai's technical explanations describe roughly 1 million sand drains beneath the first island and about 1.2 million beneath the second installed to speed up consolidation by helping pore water escape faster. But Phase 2 added a new kind of worry interaction. In soft ground, building nearby isn't neutral. Loading one section of seabed can influence stress and pore water pressure in adjacent layers. Kansai's monitoring materials explicitly note the need to watch whether the presence of the second island affects long-term settlement behavior under the first island. That's why Kansai became famous, not only for what it built, but for how obsessively it measures. Settlement isn't checked once a year and filed away. It's observed at multiple points in layers, then fed into planning cycles that decide where to regrade, where to reinforce, and where to invest in protection. Engineers track the shape of settlement where the island drops evenly versus where it drops unevenly. Because uneven settlement is the real killer. It twists structures. It changes drainage. It stresses joints. And because Kansai sits offshore, all of this ties directly into the seawall problem. As subsidence continues, the distance between ground level and sea level becomes smaller. The island's safety buffer against storm surge and extreme tides shrinks unless you actively rebuild it. So seawalls aren't built once. They're upgraded, strengthened, and in some cases raised over time, treating coastal protection as a life cycle, not a milestone. This is the part most mega project videos skip because it's not glamorous. Kansai is a maintenance mega project. Every year, the airport is not only running flights, it's running an engineering program in the background, leveling, reinforcing, monitoring, and planning for the next centimeters of movement. What makes Kansai's soil story even stranger is that the fast part and the slow part are different worlds. Kansai explains that the Holocene clay layer, the soft upper layer that can be modified, settles dramatically, shrinking to about 2/3 of its original thickness, and that this settlement ended during construction once drainage was accelerated. The problem that remains is deeper, long-lasting settlement in the Pleistocene layer, where comparable soil modification isn't feasible. That's why Kansai's future is still written in monitoring charts. So Kansai's story sets up the final question, one that matters far beyond Japan. When you create land where land doesn't exist, are you prepared to maintain it forever? If you want to feel Kansai's story in your bones, don't start in the terminal. Start underwater. Picture a drilling rig floating above Osaka Bay pulling up core samples. The mud comes up dark, slick, unbelievably soft. Someone on the deck says what everyone is thinking. This can't be right, because the material doesn't behave like ground. It behaves like food, like tofu. That's the scene hidden inside so many engineering reports, and it's echoed in the narration you provided the moment the seabed is revealed. As the primary challenge, the casing pipe is withdrawn, and a vertical column of sand is left embedded in clay, the first of 1 million sand piles. Then comes the other scene, also in your narration, the one that feels like a control room thriller. People call out alignments. They watch readings. Someone says the rate has doubled. Another voice answers, it matches the visual assessment, it's accelerating faster than predicted. And you can almost hear the unspoken fear, if the settlement accelerates, the entire island's safety buffer shrinks faster than your upgrade cycles can keep up. That's why Kansai is fascinating. It forces you to see infrastructure as a process, not a product. Most airports are built once and then modernized. Kansai is built and then continuously rebuilt in tiny, invisible increments. You don't just operate flights, you operate a battle plan against the seabed. And the battle has real stakes. Kansai's own monitoring data shows that the average settlement since the beginning of construction is about 13.66 meters, and that 9.82 meters occurred before opening. Yet the island still continues to drop, measured in centimeters per year as of 2024. So the airport responds the only way it can, engineering in layers. Layer 1, ground improvement, like the sand drains that accelerated consolidation, and lay layer early. Layer 2, structural flexibility, designing systems that can be leveled, adjusted, and maintained as settlement continues. Layer 3, coastal armor, seawalls, and protection that can be strengthened and, when necessary, raised. Layer 4, monitoring sensors and measurement networks that give you warning before damage becomes irreversible. Kansai's cost is so hard to summarize in one number. Depending on scope and conversions, reputable summaries land in a wide band, often cited around the mid-teens of billions, sometimes higher. But the deeper truth is that cost doesn't end when the airport opens. A sinking island turns maintenance into a permanent line item. And here's the detail that makes Kansai feel almost like a living organism. It has acceptable ranges. Operators don't chase a perfectly fixed elevation the way you would on natural ground. They chase stability inside tolerances. When a zone drops, they compensate. When a gradient changes, they reprofile. When a seawall margin shrinks, they strengthen the perimeter. The airport survives because it behaves less like a static building and more like a system under constant calibration. That is why the sinking airport headline is both true and misleading. Yes, the island has sunk by double-digit meters over its lifetime, and yes, it continues to settle. But the airport's real achievement is not that it never moved. It's that engineers kept it operating while it moved. It also explains why Kansai is studied as a geotechnical lesson. The project proved that offshore reclamation can support ultra-precise infrastructure, but only if you invest in ground improvement, accept long-term settlement, and build monitoring and maintenance into the DNA of the facility. So the next time you see a glossy rendering of a new airport on an artificial island, ask the question Kansai forces everyone to confront. Who pays for the decades after opening day because the sea doesn't charge you up front? It charges you in installments.